Welcome, everyone. Happy Balloween. It's a new holiday that we are creating for exactly this purpose. And you are here for the inaugural event. So congrats to all of you. You're in on the ground floor. I'm going to kick this off with just some opening ideas about why we did this event and what we're hoping to get out of it, and some organizational notes of how it's structured. And then we'll just get right to it. The goal of this is to share a bunch of ideas, and so let's focus on the sharing ideas and less on the atom blathering. So let's do this. All right, what is Balloween besides the 27th and 28th, a weird meeting that appeared on your calendars? Balloween is designed as just a fun workshop for us all to get together. It's really just a chance for us to all be in a virtual room and talk about a bunch of interesting things with other interesting people. That's really about it. If you really just wanted to know that, you can tune me out from this point on and wait till Aditya starts talking in about 20 minutes. But if you'd like to hear more, let's talk more. The goal of this is to spark conversations as well. So we're going to schedule this as a bunch of lightning talks, but we've tried to include some time for questions, and we definitely have times for a discussion at the end of the day. And I'm going to post a link to a document. We're going to capture some follow-on questions and discussions and so forth for future conversations and future workshops that we might do. Which leads me into my next point. We see this as the first of possibly many workshops related to autonomy, lighter than air vehicles, and the cool stuff surrounding both of those things. For this one, we're just sort of opening the conversation, trying to understand what is cool here, what is neat here, what is interesting here. What are the open problems? What are the principles or techniques that we might apply if someone gave us a new domain to start doing autonomy research or CPS research or hardware research? How would we even apply this? The next one, I think we might start looking about what a research platform might look like. How might we start building some of these things, doing demos, doing cool experiments that we can all put on YouTube and get more grad students and grant money and so forth and so on. So you'll hear a little bit of that tomorrow in some of our very early work, but I'm looking forward to this seeding future workshops and maybe having challenge events, who can get through the maze the fastest and so on. The output of this is primarily fun and interesting material and ideas. The thing I put together when we were first sort of throwing around the idea of this workshop is just to say, how would this team of experts, these are people that we like, that we work with, that we want to work with in the future, how would we tackle the problems of autonomous blimps? What do we think the differences are between blimps and traditional aircraft, and what's interesting about those differences? And are there new areas of research to explore based on those differences? We've all been doing a lot of work in autonomy. Maybe it'd be interesting to try a new venue to see if it shakes out any more interesting ideas or some generalization of some of our existing ideas. The one output of this event is that we would like to capture as many of these ideas as possible and sort of a summary of the workshop in a white paper authored by the group. Obviously, if you don't want to be an author, you don't have to be an author. We're not going to force anyone into being an author. And Aditya and I will take the brunt of the burden of starting it off, editing it, and so on. So, we would love to have this paper out there just as a citation that we can all use. If you ever wanted to do further work in this area, you could talk about the outcome of this workshop in that paper and cite it as a background. And as something for us to ship to research customers. So people within the US government, people within industry even, who are interested in exploring ideas in autonomy, possibly in sort of new and novel ways, and would like some, something to read first before they start investing their money. So those are really the goals. That's what we're going as output. I mean, just to be totally clear, I have a couple people that I definitely want to ship this paper out to. We would be delighted for you to ship this out to people that you know and things. And really, we just want to broaden the interest in the market in this area. So with that, you might be wondering, why am I so obsessed with balloons? Or you might not be, but the people at Galois frequently ask me why I'm so obsessed with balloons. So Let me give you a little bit of background of why balloons. So first of all, the major reason that I like balloons is because they're not quadcopters. I think in autonomy and CPS, there has been a lot of really great research on autonomous quadcopters in particular, and recently in cars and also previously in fixed wing aircraft, both individual aircraft in cars and in swarms. I think that research is great. There's just been a lot of it. And I think there might, in fact, we might have gotten a little too specialized. I'm a little concerned that, we take a lot of things for granted. We make a lot of assumptions about what autonomy can and can't do, what cyber physical systems can or can't do, based on the actual physical properties of quadcopters. For example, I think one of the interesting things is, what happens to these vehicles if you cut power? If you cut power in a quadcopter, it just falls. If you cut power to a plane, hopefully it glides down. It sort of depends on the glide stability of the plane. But, I think there are trade-offs in CPS that we can re-examine if we start looking at a new platform. And so that's one of the reasons that I'm super interested in balloons. And furthermore, quadcopters, planes, cars, we often sort of know what they're for, where balloons, it's a little more open-ended. And so maybe there's some interesting purposes that we can divine out of balloons that we want to bring to other things. So our goal with introducing balloons is really just to push a little bit outside of sort of the standard fare of autonomy and autonomy design, and see if anything interesting pops up as a result of that. So as I sort of hinted at the previous things, I think one of the most interesting things about balloons is that they float. If you take out the motor in a quadcopter, I've seen it enters into an extremely predictable ballistic trajectory, mostly going down. If you take the power away from a plane or a car, it's pretty predictable in what happens. Lighter than air vehicles float, and so if you take away the power, they continue to float somewhere. It really depends on wind patterns, which are super hard to predict. And so I think that's an interesting, different avenue of research, especially when you get into sort of low power and high endurance systems, because you don't actually have to power them to have them move. The other thing that's really interesting about blimps is that they're often severely underactuated. We actually did some experiments with balloon design in our office, and it was a really, really interesting experiment in discovering all of the airflow patterns inside our office, especially when the HVAC turned on. And so I think there are some super interesting things in how do you control balloons when there are all these air currents and eddies, and the heat and the density of the air varies so much, and you only have perhaps one fan. How do you achieve any sort of goal there? And in part of that, I think, is what's interesting is if you can connect some of the physical design with the digital design with the autonomy systems, right? How do you make all of those things make sense together in a way and have a platform that really makes sense? With that, Aditya, the floor is yours.
Hey, thanks, Adam. Welcome everyone again, and thank you for coming. Adam started this talking about the Blimp as a research platform, but I thought maybe we can go a little bit bigger before we come back. And I started digging into airships and what's the scene been there. So going from left to right, which is the arrow of time, I guess it seems after the Hindenburg disaster, we didn't really have anything concrete going on in the space. There has been a lot of, the stuff has shifted from actual designs to concepts. And there is this Lockheed balloon in the middle, which is one of the concept and also a design that has been there in production for some time, but I think it's still looking for a purpose. All that to say, the design space is huge for these things, unlike traditional stuff like quadcopter and planes. There's literally any shape, anything that is permissible. There's also, it seems that it's in search of applications. So of course there is defense. There's also this notion of cargo transport. But I think what is one of the most interesting thing to me is using airships or balloons as a base station for search and rescue and for doing long-term operations, coordinating them, which seems to me to be something that utilizes their capabilities pretty well. So apart from all the interesting concept, which is the right half of the thing, NASA apparently did a study on what's the current scene of the industry, and they wanted to assess where it is at, what does it need. And one of the remarks they had was the modeling and simulation scenario is really, really bad. There barely any tools, there barely a lot of understanding about what it means, and the entire vertical of modeling and simulation needs help. So now that we're talking about the designs of these things, and modeling and simulation is usually how I approach these things, and I guess some of the people who are attending also do the same thing. My first instinct was to go back to the traditional V model design. Now, interestingly, the question is like, why would you do that? Because that's what we've been doing it for so long. What's new there? So one thing that is new on the funding aspect of it is DoD seems to be very, very committed on the idea of digital engineering, which is just model-based design or model-based systems engineering. It's a bit more, I guess, and it's a bit over-encompassing of the entire ideas. But they in 2018 there was a document by DoD in which they explicitly say that formalized development. They had 4 goals, and one of them was formalized development, integration, and use of models throughout, not just for design, but everything for planning, manufacturing, verification, and everything. So they really want to push for models. Maybe Adam can comment on this later. Is like maybe this is just another revival of digital engineering, but I mean the model-based design. But we still have the, like, from the side of actual problem solving, we still have the same issues. We still have like requirements which are not there. What is the best way to write specifications? What are the ways to do architectures? We don't even have a common understanding of architectures. Verification, validation. There's still a question of certification. Not that stuff has been slowly evolving, but now there might be a push from the funding side to go deeper into these things. So coming back to more, I guess, a practical instantiation of digital engineering, there is this notion of digital twins, right? This is like largely a marketing term, so I'm sure everybody has heard of it now, and it means anything that people want to sell, basically. The reason it's interesting to me in this case, because it sort of pins down that modeling as a way. So it pins down a definition of model. Like, what is it that you want to do with the models, right? So this gives it some breadth. You want to go across. You want to have a model for the entire system or several models that you want to stitch together to, at the very minimum, just make them executable. And but also, if you could, we can analyze them. So, for example, the left portion of the slide is just marketing stuff. So, digital ghost is a term GE uses to talk about their digital twin. But for instance, the Air Force is looking to actually make programs that can fund such initiative, and Skyborg is one of them. I believe one of the reasons why digital twin and why now is to do with autonomy too. As we get more autonomous components, this is getting a revival. But on a more scarier and philosophical side, now the digital twin is hard. Everybody wants to use them for something, and like the middle top image is one of the very scary ones to me. Was, let's use the models of digital twins of lungs to optimize precious ventilator resources. And it made me think of the famous quote that all models are wrong. And what are they using them? So what are the models meant for, and what are they using it for? Is often not talked about. We don't often capture these details ever, that what are the models really made for, and what are they limitations. That aside, there are some interesting future applications, definitely. And again, one of the slightly scary one is Isaac Asimov's. If you psychohistory, if anybody has read the Foundation series, Isaac Asimov posits that if you model enough, you can predict the human future as a society, not on the individual level. So that is like the digital twin of a society. um, but in practice, I think digital twin is a pretty important concept, and we have looked at it from several aspects. So not just from design, but also analyzing cybersecurity of things. How would you make a special digital twin for a system that is used to analyze cybersecurity? Not just design and prediction and fault diagnosis. And there have been some interest in also adaptively controlling a system. So you base it on diagnose the current situation, adapt, and then reconstitute. So it has a multiple occurrence in several things. So going back to the system design of an airship of Blimp, which is model based, and this connects with both digital twin and system design, because what I'm really thinking about is models. What are the ways to think about models here? What are the different layers here that can work with both system design and digital twin? And this is again not really new. There has been a lot of work in, I think, 2000s, especially by UPenn and also UVA. So there's been a lot of work there, but I think there was a time when things slowed down a bit, and hopefully it'll take off again. We still have the same questions of when we have such a diverse set of components, what are some ways to even relate properties between them? Oftentimes people just go their own happy places, different domains, people in different domains, they just go their places. Somebody designs the autonomy stack. Even there, somebody designs localization, somebody designs controller, somebody designs mission planning, but there's no connections between them. Like it's sometimes even hard to connect the uncertainty of a sensor to the control algorithm and how do they affect each other. Forget about like structural, mechanical, electrical, and SOC and all that kind of integration that happens. So there's often lapse of connections between these things. So what is a good way to capture them? And we have tried to tackle some of these problems, and we are still doing it. So for example, the modeling simulation on assured autonomy, design space optimization on symbiotic design, and there has been some other aspects of hardware design that we are trying to work on. And what really doesn't help is the requirements on the left of it, which are like completely vague and ambiguous. And sometimes they're not even requirements, they're actually design decisions that they have made for you. So when I say they, it's usually when you want to get certified. So this remains an interesting and frustrating space, but hopefully with a little bit more money. So finally, what are some gaps, challenges, and dreams? So I think I already covered a bit of gaps, which is how do you connect these different things, which is design and implementation? How do we connect? How do we converge on some notions of architectures that make sense from design and analysis perspective? Some interesting progress that I thought I saw in Assured Autonomy was by Sanjit Seshia's group, which is formalizing more of scenarios, which in a way brings down requirements to something that can be tested and verified. Happy to talk more about this, but it's basically Sanjit's work on Scenic. Then there is certification, and maybe standard-based certification is not the best thing. Maybe assurance-based certification or assurance arguments is a better thing to do. So what about challenges? Again, I don't think anybody will be surprised by this, but there's a lot of fragmentation in modeling. There's a lot of tools. Every tool claims to do everything. In fact, ANSYS, which is a company that sells modeling tools, itself has 88 tools or more than that it sells. And if somebody has to design something, they have to first go to ANSYS website and say, what are these 88 tools? Which one do I need? Why do I need all of them or half of them? So it's absolutely it's very fragmented. Of course, there's a lot of modeling formalisms, endless debates on which one to choose. Also, a lot of data formats. And worst case, you don't have any executable models. You just have paper diagrams or no models. And on the modeling formalism, you have like no semantics like MATLAB famously, and undefined behavior like C or something like that. So good luck. Some of the interesting problems or really far-reaching blue sky stuff, I guess. I've listed some of them on the right side. They're not a lot of them there because space is infinite, obviously. But how can we connect the design space exploration in a meaningful way that can be used, which probably means how do you relate the different layers and different components and different domains? And how can we get multiple solutions out of it? So for example, if you have a constraint on the blimp, which is follow this kind of trajectory tolerance within, or let's say we have a mission requirement that this is the mission that should be done, you can either solve that on the trajectory tracking or planning level, or you can solve that on a control level. It's not even clear which is the best layer to solve and how do you work with it. Oftentimes we do like the best we can do at every layer, but that's not a good thing because sometimes things are just complementary. And this really shows up when you have a damage to the system because suddenly you cannot do something specific, but now you can actually do something that you could not do before. Okay, there is so the hardware, I guess Intel had a lot of good boosts when it was using abstractions that is famous in the model checking world. And I think the notion of abstraction is very underused when it comes to CPS in general. We don't have standardized way or even like some generic abstractions, even domain specific abstractions that we can use. These could be property directed because let's say you want to just test electric properties or something, then you can just split the design, slice the design in a way that you only abstract away a lot of mechanical things you don't figure out and only focus on electrical properties. But the more complicated part is when you have behavioral properties or let's say some mission level dynamics that you want to check, but it's also now based on some electrical and some mechanical properties, maybe not the digital hardware. So how do you slice the system there? What's a good abstraction of it? And can you create some abstractions offline and reuse them? Even on the dynamics side, when you have models of dynamical system, every paper presents a different physics equation for something very similar. You have to like deeply read that paper to understand what they're doing, or you have to be an expert to understand, quickly relate to what they're doing. We don't really have canonical models or even something generic. So the question is, can some generalization be done for some sort of blimp design? And I guess bringing back to earth a more mundane problem of can we have a framework to create a digital twin in which we can just create more of these things? With that, I think I'm going to end the talk.
Where would you, do you think, put that on the scale of want to haves versus some of the other things you talked about, you know, model coherence, talking about the coherence between different models, or more standards or more tooling for model development? Do you have a priority order on that in your head?
I think coherence is definitely one thing that I'm looking at. Like we have a lot of models. They're always partial or incomplete, and it's not clear what they are for. And I don't think Blimps is special in this, except Blimp is actually simpler. It's a much simpler domain, much simpler things. Everything is so much simpler that you can actually do an end-to-end things there. But yeah, coherence is definitely missing. I see something and I'm not really sure where to how to contextualize what I have. Hopefully that answers part of the question.
Yeah, and I think I'm associating my anonymous various animals and fruits with each other, but I think that was Cody who said something about design space exploration with respect to ... looking at saying something about having explored vehicular design space exploration. Maybe that was someone else.
I haven't seen the question.
That was somebody
got it.
else. Yeah.
Okay.
This was from me, Kadir. So yeah, design space exploration, we have been using this term in the world of vehicular systems, where you have different ADAS features, electrification features. So what is the optimal design with respect to energy? Now, when we say design space exploration, okay, with respect to what's the goal, what do we want to achieve, and what is our playground? That was
Yeah, I'll actually add that Ethan, Michael, and Sam will be presenting something more on that design space exploration tomorrow.
Yeah, because I think part of what we'd love to do, like ideally that we would live in a world where, you know, someone had come to us and said, we want you to explore the design space of small form factor blimps. And we could have popped open our tool and loaded up a CAD drawing and loaded up like a default, you know, battery and a default board and a default autonomy algorithm. And it would have said, yeah, that sort of all hangs together, except it doesn't have nearly the endurance profile that you want. Okay, so now I'm going to say, all right, maybe I should take a look at the CAD drawing that I created and expand the airspace or expand the power brick or something like that so that I can get the endurance I want. Wait, but then it doesn't actually work with the autonomy model in some way, right? Because all these things can affect each other and there's feedback loops across all these levels of abstraction. And so, you know, if we had that tool, that would be amazing. And we could maybe use it in other fronts when someone comes up with another wacky idea. Balloons, of course, are an extremely sensible, great idea that everyone should be on part of. But, you know, there might be a new platform that we want to talk about later, submersibles or something like that. So, but it's 9:40 and we should probably jump to our next one. So Miroslav, you're up. Let's go.
Okay, perfect. You guys can hear me?
Yes.
All right, cool. Just to check, this is the new audio setup. So with my luck, it'll probably stop working in 15 seconds. Okay, so thanks a lot for having me here. I was like debating what should I talk about, and usually like thinking about security of autonomy comes at the end of every meeting. This is kind of the first time that it's at the beginning. So I was like, okay, let's switch things a bit and let's talk about this. So when we so we've been working a lot since DARPA HACMS project. We've been working on security of control systems and then evolve like on the overall autonomy stack and in general CPS with varying level of autonomy. And pretty much the idea has always been on how can we model these systems, how can we analyze, how can we provide resiliency to them. And like with everything, of course, we would always start with a low level control and try to see like, okay, what are the guarantees, what can we provide in these types of setups. And it turns out that one of them, you can't do much only in the algorithmic domain. You really need to have this kind of combination of the use of security aware services, whether it's in cyber domain or special types of components that you would have combined with this kind of adding resiliency to the control and estimation algorithms on its own. And it turned out that one of the critical components of this kind of use of resources was of securing these systems was being able to analyze what happens when you cannot protect everything, what happens when when things start breaking for different types of attack/threat models. So one of the first things that we've done in that particular domain was looking at a standard control system. And again, in most of these applications that I'm going to cover, I'm going to focus on the ground. This was one of the scenarios with vehicle platooning. Pretty much it's easy, the easy way to for attacker to attack the system by compromising the information about the position sent to the second vehicle here in a way that the attack stays stealthy to the underlying intrusion detector that is implemented in on the vehicle. So we really can start attacking and slowly push the vehicle of its position. So the question that we started asking ourselves is like, okay, if we protect certain amount of information, what is the worst case impact that the attacker can do? And then pretty much that we use then that kind of analysis, the output of that analysis to this kind of sporadically allocate the use of cyber mechanisms like protecting the communication packets that would be sent to the second vehicle, or protecting the sensing information in this particular setup. And what we were able to show is that in this same example, that we are able to, even by protecting, let's say, every fifth message delivered to the vehicle, that we are able to have vehicle platooning, where the second vehicle would never deviate so much from its position, so that actually it hits the vehicle in front. And this in particular case is not, this is the worst case performance degradation that a stealthy attacker can achieve if he is able to compromise 4 out of 5 messages delivered to the vehicle. Of course, we can then do this in an even more aggressive way, where we, for example, allow the attacker to only compromise every 20th message, meaning that we protect 5% of the packets. And you can see this is again the worst case performance degradation that a stealthy attacker can do. And why we were able to do this? Because we were able to build a reachability analysis in this particular setup for the additional input disturbance that you can have that is unbounded, but the only constraint is that it has to be stealthy and it cannot modify only certain number of messages, meaning that disturbance only at some point has to be 0. We were able to do that because the system is linear. The moment we started moving onto real systems, it became really messy, and we had to start doing this in a slightly different manner. So we recently introduced a learning-based approach where we pretty much looked at, for example, the standard trajectory tracking that we would have on this was one of the benchmarks for Carla simulator. And what we do with the learning approach, we were able to find attack vectors that would push the vehicle off the road. So this is without attack. This is, for example, one of the attacked the designed attacks that are stealthy. They don't trigger anomaly detectors that are already deployed on the autonomy stack, but they are able to launch the attack at a certain point of time such that they push the vehicle, of course. And it turns out that it was able to find exactly at the most aggressive after the turn, where there is a high level of nonlinearity, and to exploit that to push the vehicle enough such that then it hits the other one. So it was really critical for us to have this kind of analysis that will allow us to really capture the impact of the attacker. But in this particular setup, we are still only in the standard control domain where the state space is continuous and everything is nice and something that we as a community are very comfortable working with. Then the next thing that we started asking ourselves is like, what happens when we have perception? And of course, all of us have seen these kind of problems where you have a camera and you put, like, I know, you have a stop sign, you put the stick and it becomes a panda or whatever it is. We started looking at a slightly different problem. What happens when we have this kind of fusion module, let's say camera and LiDAR and radar, and how can you spoof in this particular case such that when you have more than one sensing modality, you are able to steer the vehicle off course. And in this particular setup, for example, we created this frustum attack in this kind of camera LiDAR perception modules. Pretty much the idea is that we try to hide in the frustum of the vehicle and of the image that the camera would provide, and we are moving the points. We are moving the 3D LiDAR points, the 3D point, some of the points, only a few of them, in the point cloud, such that it actually makes it messes up with perception. And we evaluated on a really large number of different types of perception modules, different types of defenses that people have provided. And it's really what we are exploiting is that most of these defenses are looking at one-time instance perspective, meaning that they say, oh, we can detect anything within 10 meters, but they don't look at this longitudinal analysis. What do we mean by that? They don't detect things that are 40 meters away, but they say, but that's not a problem. But if we start moving 40 and then 30 and then 20, the underlying autonomy stack will start speeding up. Let's say if it's adaptive cruise control, thinking that the vehicle is moving ahead. By the time that they're at 10 meters, it's already late to do that. So what we did is we first evaluated this kind of physical insertion of attacks. And for some reason, this video does not play in PowerPoint. So I had to, so this is actually the recordings that we get from the setup, where we can see that we are moving the car and the vehicle is actually here, but we are moving it in front so that we can make this vehicle stop. Pretty much, this is actually more idea. So we have that the spoofer that we just mount on the top of the road. Well, in this particular setup, is just the high positioning, is able to insert additional points from a real car, such that this car here is actually moved to be here. And again, we looked at the impact of these types of attack on Baidu Apollo's autonomy software that was provided. The problem with that one is Baidu Apollo's does not have obstacle avoidance. So so the only thing that we could make, it would just keep on. It would not, when we insert these points, would try to avoid them. But these are fake points; they are not there. So that was actually it was resilient against attacks because it would not try to avoid even the real objects. So, for example, in the scenario that we've created here, it would just we would start inserting from this vehicle, we will start inserting points. And even if they are far away, this one will think that it's in 10 meters in front and it would immediately stop, although it can keep on going in this particular setup. So again, this was a physical attack, but now we can look at this kind of semantic attack also shows us how we can think of if we look at attacks on cyber domain and how we then can build these kind of different types of modules. What are the impact that the attacker can have, such that it propagates down the control stack, such that it can actually have the impact that is worrying us in this particular domain. So I just want to switch now to a slightly different high level of course, when we started working about perception, we started thinking about, okay, what is going on with tracking, what's going on with planning, and we started looking at the problem of both securing the mission planners as well as seeing what are the worst case impact that the attacker can have. And so in this particular setup, what we started looking at is, okay, if we have full model of the system, how can we build this kind of security aware plans that try to provide a trade-off between the guarantees that you can have in the presence of attack versus the reduction in quality of control, the standard control metrics. The problem with some of these things is that you end up having hidden information games, because in the presence of stealthy attack, you don't know what's going on. But it turns out that under some assumptions, we can move them into the standard games. Again, with the nice use of the standard security primitives, these assumptions are really easy to implement. And then all of a sudden, we can use the existing model checking framework. For example, in this particular case, we use Prism Games to synthesize these types of plans. But what if we don't know the model? Well, let's use model-free learning. The problem with that one, at that particular time when we started doing this, there was no much work, only a bit of work on the model-free learning for MDPs for LTR. So we did some of the work there. How can we synthesize in a model-free manner? How can we learn policies that maximize the probability of satisfying certain property? And then we expanding them to what our goal was, and those are stochastic games, so that we have the attacker and our system. And pretty much what we do is we move from this kind of high level specifications into suitable automata / reward structure representation that then allows us to, at this point, we even have a very scalable, very effective way of learning these types of procedures. The important thing here is also, like, moving from like just learning on stochastic games to learning for this kind of security applications is how do we capture the constraints on the attacker that are realistic with respect to the considered architecture, the considered problem, etc. So in the last 15 seconds, I would just look at what happens when we move from the ground to the air. We did a lot of work on the quadrotors, but let's move into something nicer that are balloons or blimps. The cool thing here is that under actuation is actually it's not your problematic thing. It's actually helps you recover because you have more time before the attacker makes a critical damage to your system. So in this particular setup, actually, what you can do is you can even additionally relax some of the constraints that you impose, security-related constraints and overheads that you impose on the system. It also simplifies some of the modeling assumptions that again then allows us to do more scalable approaches to learning and synthesizing these kind of procedures. So with that, I would like to thank you, and if there are any questions, I will be more than happy to.
I think we have 1 minute for questions if anyone's got a burning one. Otherwise, we can transfer over to Kadir and get him started.
Yeah, I do have questions, and you would see my presentation following up on your points. So perhaps we can catch up later on, right here.
Perfect.
Because where I was coming from, what is the baseline? Because the existing OEMs or the vehicles, they have certain security mechanisms built in, or at least they are aware of these attacks, and they are coming up with some baseline security mechanisms. When we are proposing solutions, are we taking care of those security mechanisms that are coming on the vehicles these days? Or we are making an assumption that there is no or very little security mechanism?
That is a great question. So it pretty much, it comes from, like, I know, the guarantees that you can provide come are directly related to the threat model and the system model, and control and embedded systems and the modeling community, I mean, are somewhat guilty of liking to use whatever is their favorite technique to solve this problem. And what they would then do is they would say the attacker behaves like this or the system behaves like this because it allows us to do whatever we were doing before. Effectively, what I strongly believe should be done is we have to look at both the hardware and software architecture and to capture what are the already deployed mechanisms or mechanisms that we can deploy, and how do they impact from my perspective, what is of my interest, how do they impact the control and performance of the controller and the overall autonomous systems. And then when we build reasonable model under the assumption while taking into account the real hardware and software architecture, then we can do this kind of analysis. So for example, one of the things why we started looking at this kind of intermittent use of integrity, because we were working with Intel at that particular time, and the idea was, can we add security on automotive CAN, which is already 98+% used. So you cannot protect every message. So how many messages is enough to protect? And unlike standard cyber world where you don't worry about, where you don't look at this kind of longitudinal analysis, here you do. And in this particular case, that provides you with extra slack that you can deal with. But I really think that it's very important, exactly what you've asked is, we have to look at realistic threat models, and those depend critically on the system architecture and what does the system already provide.
Yes, I think from there I will continue. I have a discussion on the mobility cyber range, which is exactly we are trying to chase this question. What is the baseline? What is out there right now? So if you can please unshare, I can share my content.
Oh, sure.
And then, so let's continue the discussion that we were just having. Correct me if I'm saying your name wrong. Miroslav? How do you say?
Miroslav?
Miroslav. Okay, yeah. So I'm also working on, like, my balloon is the automotive systems. And when I say reinventing the wheels for safety and security, we need to have design approach that has built-in safety and security, and that's why a lot of security and safety solutions are end wrapper solutions, but there is a big need of having this as part of the design. So I'm working with my students Pradeep and Harish on this, and I'm from mechanical and electrical department. Okay, so just to paint the scenario or the playground that I'm dealing with, we know that automated features will keep on adding. We have seen recently Super Cruise, we have Smart Summon, we have like I'm hearing about Ultra Cruise also. So all these features are coming as we are progressing in the coming years. And with Tesla, we are learning about the autopilot features also. That's one side is the automation. The other side is the connectivity part, which essentially informs the vehicle of what it is, informs the vehicle about the world that it is operating. It's not just the vehicle system itself, but it is talking to the rest of the system. So with this connectivity, autonomy, vehicle is getting more and more smarter, and then it knows more about its surroundings. So how do we better use this information? One more comment on the software side. As we are progressing, more of the features would be defined by the software. The software integrity is important. We know hardware, steering, accelerator, brake, they will remain, I would say, constant for a better period of time now, unless somebody thinks of something else. But those are the actuators that we'll have in the vehicle. Sensors, yes, companies are working to define their sensors architecture. More or less, let's say after a few years, the sensor architecture would be frozen, and then all the features would be essentially defined by the software. So autonomy stack, then connectivity, and this software, these are essentially evolving the automotive system into essentially computer on the wheels, or the amount of data that is being generated is also data center on the wheels now. But how do we, this all brings up the safety and security challenge. And these are some of the questions that are we are chasing. And I think I'm happy to share with all of this, the attendees, that at a component level, if you are able to assure certain safety and security feature, it doesn't guarantee at the system level. So how do we understand multiple components individually or locally working safe and secure? How do they guarantee the safe and secure operation of the whole system? Let's say we secured autonomous, let's say some ADAS feature, adaptive cruise control. Does that mean if it's interacting with other subsystems on the vehicle, will it be safe? We would like to quantify that. Because a global safety hazard may occur even if the component is behaving exactly the way it was planned for. So there are certain, let's say, edge cases that may arise as a result of even if the components are working in safe and secure. Now the other question that comes into our mind is, how do we quantify the security? It's very subjective definition. There is no metric, like, or if somebody has a metric, please let me know, because it's very subjective to the group of people that we are talking to. For some, let's say entities, it may be more of a privacy concern. For some in automotive industry, it is more of a safety concern. But do we quantify security based on the safety? Do we quantify security based on the privacy? So these are all some of the questions that I guess may trigger your neurons to think more. Now, the data available for certain edge cases or the unsafe and unsecure situations is not available or readily available. It may be available with automotive companies, but we don't have access to it. But certain reports are coming out, so that can perhaps help. But again, quantification of security in terms of safety, in terms of privacy, that's very subjective to the group of people or experts that we're talking to. Now, integrating safety and security, we would like to look in a combined way. So how do we understand, let's say, security in terms of safety? That's one of the other topics that we're looking into. there is an effort going on, but again, there is not, I would say, precisely defined way of connecting safety to security. I would say, in one of the discussions I was having, safety is to protect human from machines, and security is to protect machines from human. And how do they interact with each other? So that's something that I see it's in the definition. For now, for automotive systems, if you want to quantify their safety and security, we are working on a project. We are naming it as a mobility cyber range. Cyber range is again a concept where you can play with your system and test it under extreme situation in a controlled environment. When I say mobility, essentially it means vehicle. We are looking at autonomous vehicle. We are looking at and we are developing. We are still in the phase of it, but cyber range is a pretty, I would say, established concept. A lot of computer science people are working on it around the world. Where we see ourselves, when I say mobility cyber range, the traditional cyber range capabilities are already there. For example, you need to have some cloud infrastructure with some virtual machines, where there is an like a load distributor or orchestrator, which can distribute the computing loads or resources for automotive applications. So for example, we can look at different attack scenarios. We can collect data. We can have other AV functions. These are the green blocks that we are working on to develop. And then later on, let others interact with this and play with the scenario. We can understand with this, or with the current setting of the autonomous vehicle, we can, or the clients or the users, in our case, students, can come up with certain scenarios for attacks, which we can gather data. So this was, I would say, the overall picture of, I would say, the architecture of this mobility cyber range. In actual, essentially, it is a vehicle that we are working on, which has some actuation capability, which we are saying as a drive-by-wire kit, that can interact with NVIDIA Drive, which is the AV software stack computer. Essentially, it interacts with the sensors. And we are trying to deal with the actual, let's say, as actual in baseline as we can. So dealing with 8 radars, 8 cameras, there is sensor fusion going on, then perception, localization, control algorithms are being developed. I would say we are still in the process. We are not there to establish this baseline, but we are working on this. Then we have the connectivity element from OBU to, let's say, we are trying to issue commands to the vehicle. Now that we can drive the vehicle with a joystick, we are trying to make it to drive wirelessly, which essentially is the connectivity part of it. So a vehicle with, let's say, autonomous sensors, sensors with autonomous functions, and then connectivity with some actuation commands. So Diti, I will have one more slide. I will stop after that. Some of the experiments that we did was essentially, okay, what the easy way, what we found was sensors are the most prone or vulnerable components on the vehicle, because all of the security mechanisms are sitting on the perception or ECUs or the computing units. So if we are able to spoof the sensors, perhaps we can do the, let's say, a considerable or some damage that is noticeable. Yeah, so we started playing with this. Let's have one camera and see if we have a baseline perception neural network, and what are those situations where we can mess up with the perception capability. So stop sign was one of the critical signboards. We looked into certain situations where we were able to come up with certain situations where we can result into wrong interpretation of stop sign, and that can result into safety hazard eventually. Now, whether you can call it as a cyber attack, I won't say that, but it was an adversary that can result into safety feature. Now, this is, I would say, one of the first attempts that we have done on the mobility cyber range. The intent is to make the mobility cyber range as rich as we can in the attack vectors, and then play with those attack vectors as much as we can. And with this last statement, yes, this platform is, I don't have any NDA with any company. So this is all, let's say, openly accessible. I would welcome if anybody wants to perform their say algorithms or experiments on this. We can talk offline how to take best use of it. So I will stop over here, and then perhaps we can have some discussion.
Any questions for Kadir? But any other questions that we want to ask before we switch over to Cody? All right, hearing none. Cody.
All right, sound check and video check. Okay.
Both are good.
Good. Yeah, so I spent a little time thinking about balloons, and then I had to admit that I don't really know anything about balloons, dynamics, controls, even what applications are. And I also looked at the list of speakers and all the expertise on controls and autonomy and formal methods and security and stuff. So I decided to actually talk about something a little bit different, which is air traffic control. So I've gotten some answers on this. What are we doing here talking about balloons, especially Adam with your intro. And I guess we'll learn more as we keep going. But one thing that I think about with my research is how aircraft actually fit into this larger ecosystem, right? And so I study everything from how an aircraft actually leaves its jetway and then makes it all the way to the end. And so with balloons, there's some interesting questions, and I'm not really going to get into that now, but just talk a little bit about how autonomy fits into the fact that there is a larger airspace. And I think even with military or other types of applications, this is this is a valid thing to think about. If you've ever been to Langley, Virginia, you see all the F-18s flying out of there. Those are all controlled by an air traffic controller. Or if you've flown out of Orlando on a launch day when they're launching a rocket, the air traffic controllers there actually have to modify how the aircraft flow, because there's this big explosive thing that's taking off 80 miles to the east. And so we could think about how balloons are integrated in a bunch of different ways. Just as a little bit of background for this group, air traffic management has had several major pushes to modernize. You know, this system, a lot of what we rely on in terms of infrastructure is 70 to 80 years old. And so we're trying to modernize and actually get not only the equipment, but the algorithms and decision-making procedures up to the 21st century. Most recently, and a lot of where my research in this area comes in, came out of this program developed at the FAA with NASA and EASA and a bunch of other organizations called NextGen. And the idea was, as part of this modernization effort, having a co-optimization to reduce environmental impact, reduce noise, increase throughput, and do all of that while maintaining safety. And a big focus is on the literal definition of autonomy. So this is from, I guess this is from Oxford Dictionary, right? So the right to self-government or independence. So this idea that we're going to manage the airspace such that any entrant can actually self-govern or have independence, right? So if it's a Delta flight, if it's a United flight, if it's Lufthansa, or if it's a balloon, that to the extent possible, I can actually do whatever it is that I want, getting from point A to point B. And how do we do that, though, in a safe way? And so the idea here is that we have a bunch of tired pilots and a bunch of tired people behind the scenes who are doing all the operational decision-making for the airlines. And then we also have tired air traffic controllers, right? So an air traffic controller today, actually still today in the year 2021, essentially has to give discrete commands to every aircraft at different points in time throughout its flight, right? So I'm not flying much these days because of COVID, but take an average flight from, say, Chicago to DC, that flight will receive dozens, if not hundreds of instructions from the air traffic controller, right? And so the controllers are doing this for every flight. So it's kind of a crazy system. So one of the concepts is to go to this notion of what's called performance-based navigation. And I see on the chat, there's some questions about what can you do? Can you actually navigate a balloon with any kind of precision given winds aloft and other kinds of weather? The idea here is, let's take a typical aircraft, like a 737, is can I actually give a kind of certificate to the air traffic control system where here's the flight I'm going to take, and this is a 4-dimensional trajectory. So here's where I will be in space and time from when I take off to when I land. And if I can achieve that within some kind of uncertainty bound, then I can manage the overall traffic in a different way than what I'm currently doing. So instead of saying, once you get to the top, you have to head in this vector at the speed, I'm actually just managing a bunch of trajectories and making sure there aren't any overlaps in these. Again, this is a 4-dimensional, so 3 dimensions in space and then in time. So how to actually do this? So how to take advantage if we could have a certificate around our ability to navigate in space and time, how would we use this from an air traffic control perspective? Several concepts use the notion of time. And the idea is if you are an aircraft, you could give me a couple discrete locations and then time windows in which you'll be there. If you can give me that type of certificate, then I can manage this complexity and keep all the aircraft separated. This isn't my idea. This is just a very high level concept. So our research was to come in and actually generate algorithms for where you would actually place these locations, what the time window should be, and what kind of guarantees you can actually get in terms of separation. And so you can imagine I'm going to come in now with a balloon and maybe have just a lot worse performance, right? So I'm going to try to get to this point over here, but I don't know when I'm going to be there, and I might not hit that point. I might be a mile off, right? Well, that's okay. As long as you can bound that uncertainty, then I can manage all the other aircraft that are more traditional around that and still have some notion of efficiency and safety. So I'll skip some of these details, but the basic idea of where we want to go with air traffic management is this is 4DT management. So this is a little bit of a grainy picture, but this is basically these windows in space, and then you have scheduled times of arrival. And then if you know something about both forwards and backwards reachability, you can basically have a manifold around if I know where the aircraft is now and I know where it's going to be in 5 minutes, then there's a manifold of spaces that it can actually reach in time. And I just need to make sure that those are deconflicted. And those might be automatically deconflicted based on constraints in the dynamics, or I might have to intervene, right? So the idea is again, the dictionary definition of autonomy is I can, in certain cases, just let you do whatever you want as long as you get from point A to point B in a certain amount of time. And so you can burn all the fuel you want, or you can take your time, whatever. And so now we can think about possibly, so I imagine this is going to be a big headache if we start flying balloons around San Francisco or New York or DC. And so I'm here to sort of maybe start thinking about how we would get this integrated, how you'd get, it's a little bit applied just from a policy perspective, like how you would get the FAA to buy into this, but also from an autonomy perspective. And with people from, who are even on this call, who are into formal methods, you could start to write down like assume guarantee contracts and have that integrated into this larger framework where we have different kind of contracts on different types of aircraft. So the basic idea, I'll get into a little bit of the technical stuff then, and then I can wrap up. So here's a heat map of basically trajectories. I think this is the Utica sector. And so you see that basically the way that air traffic works is there are a bunch of flows, right? Which makes sense, right? There's big population centers and people want to go between population centers. So the red line kind of going across horizontally is, I think, probably New York to Chicago, Detroit. And then you see sort of lines going off in other directions. So then the question is, can I manage flows of aircraft sort of all going in the same direction? Can I manage those in a way that's preserves some notion of forward invariance? So if it's safe now, what kinds of structure can I impose on the problem such that it'll be safe for all times into the future? So flows and then crossing patterns or merging patterns, right? So I have to manage this flow here, make sure that the aircraft are separated, but then I have to manage this crossing pattern here, and I might have aircraft actually merging into this flow because they want to head off to Chicago. And so it turns out that crossing patterns are really easy to manage in terms of safety and verification. Diverting, so aircraft are on a flow and they're going to split apart. That's obviously really easy. And it turns out that actually in-trail flows and merging, if you can figure these things out, then you basically solved 99.9% of air traffic management. And so we've kind of been looking at detection. So can you detect in both flows and merging sequences where you are guaranteed to be conflict-free when you only provide a future point in space and a time window when it has to arrive there? And if you can, there are scenarios where you can do that and guarantee that there will be no collisions regardless of what the aircraft decide to do in the interleaving period. And then you can identify this middle case where you might actually have to impose a little bit more constraints on the aircraft, right? So you give it a four-dimensional time, 4DT waypoint, excuse me, and then some speed advisors. You have to speed up or slow down. And then there are cases where you're guaranteed to have a conflict and you have to do something a little bit more complex in terms of intervening and sort of taking away the autonomy of the individual aircraft. And so we're looking at methods that here's a scenario where, so it's the vertical dimension is actually positioned along a flow, and we have 3 aircraft, and just using notions of both forwards and backwards reachability. So this is a time in the future, and then these are positions in the future along the flow. And you can see that in this case, there's going to be, based on reachability, there's going to be some overlap. And so in this case, you might have to impose a speed constraint on one of the aircraft. And you can do this in an optimal way so that you're minimizing the amount of infringement on each of the aircraft. So this is just a little bit of pseudocode algorithms for how it works. I don't think these details are terribly important. It's more of just the concept of integration within the airspace. So so here are things that we can prove. But one thing that we're doing is we're assuming traditional aircraft, right? So these are fixed wing. They can be different, right? So you can have a 777 or a 737 or Airbus 380 or whatever. But they all have similar types of dynamics. So what would we do now if we had, obviously a vertical takeoff and landing aircraft behave differently, but now what about balloons? I don't know anything about the dynamics of balloons and then weather and all of that stuff. So that's kind of an interesting thing. But we can start to get into a contract type of framework, which I think is interesting, again, given the group of people on this call. So I also just want to mention something that I know several of you are very familiar with already, but we're thinking about advanced air mobility. So this is actually a good time if we're not thinking about military applications, but we're thinking about more civilian side, is like, I haven't seen anything about balloons in advanced air mobility concepts, but this is interesting because the community is actually thinking about how these systems are going to change, and that we're already going to introduce novel aircraft types into urban environments, for example, with increased traffic density and other societal factors. So what about balloon dynamics? We might as well, this could be a missed opportunity if you're interested to leverage something that's already going on. So with that, I'll just wrap it up, and I glossed over a bunch of technical details, but that's fine.
Thanks, Cody. Any questions for Cody before we break?
I can ask one. So this actually reminds me of something NASA had maybe like a few years back. They call it something like highways in the sky, or sky highway something, which I thought was a more rigid manifestation in which you already have these routes. And I guess you could have these highways depending on, are you a commercial airliner, because it might map to holding patterns that aircraft typically take over airports, and some routes that you also showed the heat map for. So they already exist, and depending on the capabilities, you would just map it. So you're not like doing reachability analysis online and negotiating a new route. You might have a set notion of highways, so that you can map your aircraft into depending the capability you have. So maybe F-16 can go in other one, and commercial airline other one, and balloons can go in other one. So my question would be like, is that something that makes sense? Is like that the next step, or are we jumping directly to this kind of stuff?
That's a really good question. So that, as far as like advanced air mobility goes, that's an open question of like, what does the structure of the airspace actually look like? Right. So there's everything from free flight. Like if I'm going to take an Uber air taxi, I just go to the top of the nearest building that has a vertiport, and I fly to the vertiport that's nearest to my destination, and it just flies directly there and does collision avoidance. That's on one end of the spectrum. And then the other is, there is active research on this sort of corridors, which can be abstracted in different ways. So there's one version, which is Uber would have its own corridor and Lyft would have its own corridor, right? And then when it has to go down to land, there's some crossing over, right? So that's the same type of aircraft, but allowing different highways for different operators. And then there's the one that you said, which is different aircraft types might have different corridors. I actually am working on a paper right now that's trying to compare sort of the types of control policies you'd learn in terms of collision avoidance with different assumptions on airspace structure, right? And how dense you can actually go. So there's claims on like, we could have X number of aircraft takeoffs per hour, and we can handle it with this collision avoidance algorithm. But that's all conditioned on assumptions about the structure. And so I'm trying to look at that. So the long answer. Short answer is it's an open question, and people are looking into it.
Thank you.
All right. Ufuk, if you want to start presenting, you can.
Okay, so thank you for organizing this. So as probably a lot of people did, last Friday, I was thinking, what the hell should I present? What the hell is a blip? And then I opened Galois website, this workshop website, and Adam and Aditya, I thought they anticipated that we would have no idea what we were going to talk about. And they put some buzzwords. And I started reading it, and then I realized, yeah, maybe some of these buzzwords I can probably connect to it. And I found this paper that we had recently. It is essentially looking into energy constraints, energy issues in planning for Markov decision processes, and the stochastic uncertainties I thought would hit on the large environmental disturbances aspect of it. So I'm going to talk about that. So let me start with a model. We will be working with Markov decision processes, as I'm sure all of you know. Finite set of states, finite set of actions, stochastically realized transitions. And then we need to keep track of the energy level of these systems. One model for that is the so-called energy and MDP. It goes and expands the tuple that we have and puts this energy function, exchange function. It's essentially yet another function over the edges that we see in the graph. And it goes and increments or decrements some counter that you have. And you can start asking questions like, just the usual questions that we ask in MDPs, while also respecting some constraints on that energy never goes below a certain level that you don't like, for example. The issue with these things is that there's no polynomial algorithm known for energy MDPs. So instead of those, we will work with a relatively similar model, so-called consumption model, which was introduced about a decade ago now. It's going to remove this energy exchange function, and it's going to put a consumption function. The difference is that it is going to be able to decrement the counter, but it's not, the edges cannot increment. Instead, there are these dedicated states for reloads. When you go there, you can go and reload whatever capacity that you have been using, and there's a bound on that resource that you are using. There's a cap. If you go to a reload state, you cannot recharge more than that cap. So it turns out that we looked into this problem from the angle of strategy synthesis for some set of objectives. Almost sure bookie we looked into for these consumption MDPs, and then we realized a couple of things, and we saw that actually we can develop a polynomial time algorithm that can take care of these, an algorithm that can take care of the following three sets of objectives in time polynomial in the size of everything that we have in the model. The first is safety, and in this context it is just avoiding exhaustion. I'm sure you can put additional safety constraints over the states of the underlying MDP. The next one is so-called positive reachability. Essentially, you stay safe and do something useful, be able to reach somewhere. And then once you have this positive reachability, you can actually go and iterate over that and obtain almost sure bookie conditional satisfied as well. The algorithm essentially goes and keeps track of the energy that you need to be able to survive, and then positively reach something from every state. And it is essentially an efficient way of bookkeeping that information. And one note, a little note here is that even this middle objective that we have, this positive reachability, I'm trying to make that comment because if we were looking into only Markov decision processes, we wouldn't need memory to be able to keep track of all that. But in this model, it turns out that memory is necessary even for this little step, which actually shows that this is simple, easier to deal with, obviously, than energy MDPs, but it is also strictly harder than plain conventional Markov decision processes. So that is what we had been able to prove, and then the results were fine. Obviously, they were respecting the theoretical guarantees that we have, but also the problem formulation does not look into certain aspects necessarily, and we try to also wrap some heuristics around it so that the results are not only theoretically useful, but also practically they look nice. And then a former postdoc put these things into essentially packaged them and called it the toolbox. And it allows us to do certain types of analysis we already have done. You will see some of these animations. I think the orange places are the reload states. It is trying to get to this green thing. The blue is where the agent is, and there is the underlying stochasticity. It does things sometimes not in an expected manner. So it just creates behavior like that. And on the right, we had been looking into the capacity of the agent versus the number of time steps that it takes. Obviously, as the capacity of the agent goes on, it increases the number of time steps that is required to reach the target states reduces because it can do without reloading. And then we can create qualitatively different types of behavior when the capacity is low or high. What we see is that if it is low, it has to keep an eye on the possibility of exhaustion more seriously and stay around the reload states more. What else can we do? So this is the amount of randomness in the environment in the MDP. There's nothing unexpected here. If it is low, we can keep the number of time steps to complete the mission for uniformly for different capacity levels low. But if there's uncertainty, then you have to account for it. Either you have to have larger capacity, or it is going to take longer time to complete the mission. And then we can go and have a bunch of reload states and bunch of targets that the agent can, we may ask the agent to be able to do all these things. And the animation on the right is showing one instance of it, and the figure on the left, I just realized that I don't know how to read it. It's just the dots are all over the place, but this is essentially trying to show that as the number of reload states changes, we can compute things, and we get those numbers. And these graphs are obviously empirical, that we run a bunch of things and take averages over them. We try to smoothen for the underlying randomness, but or random generation even of the MDPs. But there's still those glitches. Not every trend might be interpretable. So the next thing that we did out of this work is, can we compute anything in multi-agent settings? And when I put this title, and then I thought, like, do we actually have, how many blimps do we have in the world? And it is actually a much lower number than I had thought. There are this Google source claims that there are only 25 blimps in the world. So if somehow all the blimps in the world come together and there's a blimp convention, can we actually control them? So we looked into this, and the starting point was multi-agent planning to minimize the mission time is a very hard problem. So the starting point was that. Then we realized that if we give up on the time, which blimps seem to have quite a bit of time anyway, but minimize the resource capacity required to complete a mission, then we can actually, we have been able to find an algorithm that again runs in polynomial time. This time actually in the number of agents and targets as well. There's some neat decoupling. And then on the right, there's an animation here that shows that we can animate them, dots can move. But on the left, what we see is that the number of targets, you can relatively easily go to hundreds of blimps. So if we can manufacture more blimps, the algorithms will be able to handle them. And the computation times seem to be relatively actually manageable. So with that, just a little summary here. The summary of a summary talk is, I'm just going to skip that part, but I think this is just the tip of the iceberg. If we try to understand what kind of uncertainties missions with these systems might be subject to, there might be quite a bit of that we can look into with a hierarchy of different models into just to an abstraction to the digital twins, for example, Alicia was talking about. I'm going to stop there. Thank you.
So any questions? For food? I mean, one question I always have, and I admit this is a failing of mine, is how I layer. So as someone whose background is mostly in systems and networking, when I think of states, I tend to think of them in terms of program states rather than in physical places in the world and transitions between those two things. And so I always have a little bit of a hiccup when I'm imagining these sorts of models in to what level of abstraction am I mapping those states to the world? Am I mapping that to system states in the sense of engine on, engine off, engine running at this speed? Or am I mapping them at, as the previous speaker said, as like 40 points in terms of space-time? Or both?
I interpret it as even probably in a much less actionable way. My version of it, everything, a snapshot of everything that matters to reason about whatever you are trying to reason about the system and the properties that you have in hand. So it could be things that are anchored to the space that we see, or it could be the things that are hidden, health conditions of the things that might interfere in the execution of your system. It might as well be the configuration of the computing algorithms or computing hardware underneath, just if it interferes the execution of your system to a point that matters for what you are trying to reason about.
Yeah. Yeah, and one thing that I think, I know Aditya have talked, and I have talked about it a couple of times, and I think is one of the hallmarks of his talk, and this notion of intermodal coherence, is layering these different decision procedures across each other. So I have a planning algorithm that is determining how I achieve my high level goal of going from here to there, possibly refueling along the way and achieving these sort of mission outcomes. Then I also have sort of lower level probabilistic effects of what are the winds, air currents, and other things that are going to impact that as I'm flying from a moment to moment perspective. And then I also, in some of the jankier aircraft that we have dealt with, have some probabilistic expectations that this actuator actually does what we think it should do. Because, every once in a while when you're building hobbyist style things, your flap does not in fact deploy, even when you tell it to very reliably. So, layering all these models together to come up with a universal state space that you can then reason about in these ways. I don't know that, is there work in this area that we could look at or cite or consider?
Just all these people?
Yes. All right. Well, congrats. We've brought all the people to the right event, and we'll have this problem solved by tomorrow afternoon. So that's going to be awesome.
Let's define the problem first. What is the
Yeah. First, define the problem so that it can be solved by tomorrow afternoon, and then we'll work from there.
All right. Yeah, that would be good. Thank you.
Well, great. Then
I have a question.
For the record,
go.
I unshared my screen. All right. I think I need some phrases for that too.
Hold on. Everyone applaud. Very nice. Very nice. Someone had a question.
I did have a question. Hi. Can you bring your screen back, like the last slide that you had there with the no?
I don't want to lose this. I'm bringing.
You had this.
You were asked. We'll give you a card.
Picture of open problems and where things are going, and what is the significance of the colors, the red and the blue ones? Like, is it just annotations, or this is indicating current progress or current? What is the status with POM-TPs? Let me be more explicit.
We can talk about it, but I think things are going well.
Good to hear.
You can do a lot. You can always overwhelm an algorithm. You can always just like blink of an eye, you can create unmanageable things. But I think compared to 5 to 10 years ago, here's what it's Georgios. I picked these things and I left some of the other stuff out. Why did I pick these things? Because I picked them because I have things to say about these versions of them, right? Yeah, I would say things are going really well.
All right. Good to hear.
But let me take that offline.
Okay, sounds good.
Yeah, I can share a couple of things with you and my comments on it. But yeah, okay, you can be hopeful.
Yeah, thanks.
We do have a discussion session, so we can definitely discuss those things.
Sounds great. Yeah, I can pick it up and I can share a couple of pointers. Yeah.
Apologies. Is it Choo-Choo?
Yes.
All right. Note to self, next time you organize a workshop, make sure you know how to pronounce everyone's name before you start announcing.
Yeah, my name should be easy enough. I haven't really seen anyone who pronounced my name in the wrong way.
Good. Me too, by the way. So it's really nice, isn't it? Yeah.
All right. Thank you. Hi, everyone. This is Choo-Choo. I think most of you already know me, but for those of you who doesn't know who I am, I'm a system professor, joined MIT Aeroastro last year. And I graduated from Illinois Urbana-Champaign with Professor Shannon Mitra in 2019. So today I will briefly, at a very high level, talk about a few of our recent works on verifiable neural control synthesis with neural certificates. So what I mean by neural certificates and neural control is that instead of, when we use machine learning to find control policies, instead of directly finding a control policy, we actually divide our learning into two parts. One is a neural certificate, which can serve as a proof for some desired property. And I will talk about a few of those proofs, how it will look like, and we will jointly find a policy. So the policy is learned to make sure there exists a proof. And of course, because the proof is learned for formal verification people, this is not a valid proof. We'll have to develop some verification techniques to prove this is a valid proof over the entire state space. And if that's done, the policy can be used in closed loop with the plant. And moreover, if there are environmental changes or some uncertainty that occur, the proof can also serve as a monitor and it sort of to adapt the policy to make sure the proof always hold. Now this is like the high level picture of what we mean by neural policy and neural proof. And there are a lot of people working on generating neural certificates. And closest to ours is this first paper by Sichun from San Diego, UC San Diego, on neural Lyapunov control. And the work I'm going to present today is going to align pretty well with this Europe's 2020 paper. So before I talk about a few of the proofs, let's take a look at the existing approaches for generating a sort of certifiable or robust control policy. We can use robust model predictive control. That's really what industry people would do nowadays, but it needs significant online computational time. There is an explicit MPC where online computation is fast, but that is really a very complex problem. Most of the system we are looking at is impossible to construct the explicit MPC policy. We can use sum of squares as one of the most commonly used method to generate a certificate. But for us who have worked with sum of square methods, we know that the complexity of solving sum of square is going to grow exponentially in terms of the problem size. Normally, we do not expect to find a sum of square certificate for a high dimensional system or system with, for example, partially modeled as a neural network. We can use more than machine learning methods like constrained reinforcement learning, but those methods lack of guarantees. They generalize poorly beyond training data. And the benefit of neural certificates is that it can enable fast online computation. Ultimately, it's just evaluating some neural network policy. And it can provide formal guarantees. I will show you how those guarantees look like. And it can generalize to changing models. So let's use this very simple motivational example to illustrate what I mean by neural certificates. This is a example problem that a lot of you might be familiar with. Basically, there's a blue tracer satellite that's trying to dock to the black target satellite. Now the safety constraint says, first of all, this docking has to happen within a certain amount of time. And when the tracer, the blue one, is getting close to the black one, like within the circle, green circle, it shouldn't approach the target anywhere else except for the green corn kind of region. So this is a non-convex safety region. And there are model uncertainties. For example, the target satellite might move unexpectedly. And the coordinate is centered at the target, but the target itself is moving. If there is unexpected movement in the target, then the whole problem has environmental uncertainties that can get introduced. If we abstract this problem, the goal is to find a control policy that is certified to let the chaser satellite to perform some sort of safe reach avoid tasks under uncertainties. And if we are going to construct a certificate for it, there's something for control theory called control Lyapunov barrier function, and it can serve the purpose for certifying a safe reach avoid task. So a control Lyapunov barrier function will have 5 sort of requirements. It's actually not difficult to understand. It's a single function V. If we take a look at the first, second, and the final requirement, it's basically the Lyapunov function. It says the chaser will dock to the target within a given amount of time. And if we look at the third, fourth, and fifth bullet, it's a barrier function. It says this function should always be within 0 to some threshold C when in the safe region, and it should be greater than C in the unsafe region. And the final one is like a shared requirement. Basically, it says the value of V should decrease along the trajectory. Now, this is like sort of a certificate, what we want to construct. Of course, it's very difficult to construct in the sense there are a couple of bullets we need to satisfy. The safe region is a non-convex region. And there could be model uncertainties where we encode it here at the last bullet. But if we are going to use a neural network to represent this V, and of course, the control policy at the same time, all these 5 requirements can be easily encoded in a single loss function. And that's the loss function I showed at the beginning. If we have done that approach and take a look at what we have learned, this is a contour map, of course, the 2D version of the contour map of what we have learned. If we look at this map, first of all, it's guaranteed that the system, this satellite, if it starts within this ring between the 2 green regions, and of course, including the corn region, it will never leave it because the trajectory will always go to the darker place of the state. And if we look at the darkest place, it's not that obvious, but its darkest place is exactly where the target is. So this certificate tells us that our policy will make sure a satellite will always dock to the target. And if we look at the comparison with other methods, the orange one is ours. The moving target could lead to a lot of uncertainties like the mean motion of the satellite. But if we change some of the parameters, of course, the algorithm doesn't know the exact parameter. The orange one is ours. It can always have a safe docking. But we compare with other methods like Hamilton-Jacobi, it's the purple curve here. If we read the purple curve, Hamilton-Jacobi has always been overly conservative. So it will never lead the chaser to dock. It will just stay away because the target is too close to unsafe. And if we look at robust MPC, it's sort of fine in the normal case, but when there are model uncertainties, the chaser will just fly away. And if you look at constrained policy optimization, one of the constrained reinforcement learning method, it will just completely ignore the safety constraint and get into this forbidden region, the white region within the green circle. And we can do a similar thing for vehicle tracking. This is a car that's trying to track some reference trajectory. The car has a friction in the tire. And if we look at the relative distance of the car versus the reference, what we want is that, of course, we want the car to converge to the reference, or the reference is a moving target, but this is just an instance of it, sometimes instance. And we never want the car to deviate too much from the reference. So if we learn a control Liappmann barrier function, we'll have something here in the middle, and compare with robust MPC, we can always constrain the maximum deviation of the vehicle with respect to the reference. And if we compare this with robust MPC, we can achieve a 100 Hertz of control, while robust MPC, if we run it in the middle at 10 Hertz, it's less than real-time computation, although it's performing well, but you cannot really use it because the computational time is much longer than the updated time. But if we do real-time computation, then on the right, you see the vehicle just deviate a lot from the reference that it's trying to track. We can also do this for a neural network model, where here we have a drone that's going to land in a strong wind. So there's a very complex aerodynamics that is learned as neural network. So the whole drone is modeled as a nominal model plus a neural network, and we want a smooth landing. This is the barrier Liappmann function we have learned. We see that the drone will never fly away. It will always smoothly get to the surface level. But if we look at robust MPC, it will actually keep the drone in the middle of the air instead of letting it to land. We can build the neural proofs for multi-agent systems, and even for systems that have a model that's learned from data. For example, if we look at some human model from traffic, like that cyclist trying to get across this street that's in front of a roundabout. Of course, there are human-driven cars that decide when to make a way to the cyclist, when to enter the roundabout. This information I learned from data, but we want to enforce some sort of reasonable behavior using neural proofs in a multi-agent system. Of course, we have to assume each of the agent has a limited sensing range. Like for the cyclist, they can have this circle at the sensing range, and they can observe where are its neighboring agents, but this observation is going to be a time varying and this quantity and permutation varying problem. We can build such a certificate. And for example, in this case, I'm showing two screenshots. One is a intersection with a lot of pedestrian. The other one is a car with, it's a roundabout with a lot of cars. For any time instance, if we add an agent to this scenario, for the agent, what they have in mind is this neural certificate that I visualized on the right of each scenario. Basically, if we simply look at this, the certificate says the newly added agent should always go to the bluer area of this thing instead of going to the more red, because we learned a decentralized barrier function. The barrier function will always make sure the value on this heat map is positive, and it wants to be more and more positive. And if we do this for different data sets across highway or roundabout or crowded intersection, we can observe some really interesting scenario. First of all, the model is directly learned from imitation learning, but compared with pure imitation learning, if you look at the left, the agents are much more reasonable. Like the pedestrian, when they are making a way to the car, they will not squeeze together. At the roundabout, the cars will like really nicely track the roundabout instead of going all over the places. At the crowded intersection with different kind of models, the cyclist will not get across the pedestrian. And finally, on the highway, we can reduce a lot of those unreasonable behaviors, and everything follow the same framework. More importantly, this kind of model can generalize to unseen scenarios. If we put a car that the learned agent never saw before, so this car running from right to left was never in the training data. Now, if we ask the pedestrians to move according to fixed trajectory or imitation learning or our method, we can see that only in our case, the pedestrians will make a way to the slowly moving car and still going to their destination. But in other cases, pedestrians sort of completely ignore that there's a car trying to pass through the street, and it could go all over the places. And finally, I want to say this neural certificate idea is a really powerful tool. It can support a lot of different cases. For example, across all these different cases, we are using the same training framework. For example, on the left, the top corner is like more than 2,000 drones in a city to do the delivery drop. Every drone is implemented the same decentralized collision avoidance controller with a certificate. And the certificate can be assembled all together to give us an overall safety proof. No matter how many agents you put in the environment, you have a strong proof of safety. On the top right corner, it's like a screen. It's a tiny corner of a big seaport where there are more than 1,000 trucks trying to deliver things across containers. And of course, we can have like this traffic scenario where the models are learned from traffic data, but we build neural certificates to infer some sort of basic constraints from them on the learned models. So that's all I want to talk about today. Sorry, I'm going a little bit fast. Here's a list of papers that I sort of mentioned in this presentation. Thanks, and if you have questions, feel free to let me know, and or just send me an email.
Anyone have a quick question? Or does anyone have any slow questions?
Quite a few questions. One question would be, normally when we do control barrier functions and Lyapunov certificates, the kind of controls you'll get will be very different performance-wise from MPC. MPC would have like a much preferred performance, but no guarantees. Is there? But what the simulation I saw was like really nice. So was there something else there?
The quick answer is no. There's nothing, no trick that we are playing here. I'm not sure what kind of weird behavior you refer to, but sometimes the Lyapunov control policy, a barrier control policy, if you use the quadratic program to solve it online, it could be very like non-smooth. But there are always ways that you can add to smooth the control policy, because Lyapunov or barrier function kind of give you a large set of possible policies that satisfy this requirement. You can always try to find a smooth one that is, for example, we can have a nominal controller that's given by MPC, but it has no guarantee, and you only update the MPC controller so it satisfies the neural policies that you have learned. So in that way, you can have a policy that's really close to MPC, but it will fix all the non-guaranteed part of the MPC control policy.
Yeah, that's
Mhm.
actually where my I was also thinking that would be a
Mhm.
nice marriage of both of them. And I've seen like some results on MPC can retain their feasibility if you use the
Yeah.
constraints from Lyapunov barrier functions. Although I do not know how they work in practice. Thank you.
Sure.
I don't
Do you
actually have
other
a question, but
questions?
I was
Yeah.
actually curious how this your talk there and also Cody's talk could connect in some way, because they both seem to in some way be speaking about the constraint space of a vehicle that you may or may not know or that you are generating. In the sense of maybe I could provide the models that you are generating as part of this to an air traffic control system and say, this is the model of my believed behavior, and these are the constraints that I'm going to plan to stay in. And to what extent ATC would want to consume those sorts of models, or those models would be helpful or not.
Yeah.
I'm sorry.
Oh yeah, I was just gonna say that there is a comment in the Google Doc about what I used for the reachability, and I was using pretty conservative outer approximations. So having something that's tighter actually gives more efficiency back to the airspace, right? So sorry,
Yeah,
I
I
interrupted.
mean, go ahead.
Yeah, sorry. What's the question again? I sort of didn't really capture the question.
Well, I was noticing, in Cody's talk, he was using, it sounds like fairly coarse estimations of where a plane could be between 2 points in terms of deconflicting airspace. It seems to me that you're generating a much more precise model of where an airplane could be and wants to be as it transits from point A to point B. And that there might be an interesting connection between those two things, both in terms of allowing better understanding of the airspace, but also perhaps stronger guarantees of the safety of the system going forward. I will admit that I threw in a little bit of things that I've recently been interested in, which is, how does a human ATC person, either at a level of policy or in a tower, accept the model that you just provided, which I presume is fairly complex, as probably true, and what guarantees. So anyway, it just popped in my head while you were speaking that these two things might be interestingly connected.
Sure, sounds good. Yeah, thanks for the comment.
Can everyone see my screen and hear me?
Yes, yes, and yes.
So, okay. Yeah, so I thought about the talk or the topic today, since I'm also not an expert on blimps. So I thought maybe I should just mention some of the research activities I have done so far, and then try to see how much we can leverage from the work I have done. So I'm from Utah State University. I'm an assistant professor at the Department of Electrical and Computer Engineering. Let me just summarize, my research activities first. Basically, they are all centered around these two themes. So the first one is where we apply formal modeling and verification techniques to real-world system designs. Specifically, we have been interested in these three areas, namely, deep neural network verification for image classification tasks, neural network on chip systems with application in cyber physical systems, and also synthetic biology. So so I'll talk a little bit more about the first two activities. For the third one, I thought it might be a bit further away from the topic today, but basically what we do there in the synthetic biology is that we actually build probabilistic models, namely the continuous time Markov chain models, to basically model chemical reactions that govern, DNA translation and transcription, and they actually have a lot of behaviors that would map to digital circuits, like oscillators or like logic gates, etc., etc. So we actually use probabilistic model checking to to verify some of the critical properties in that area. The second theme is on the algorithms and tool development for scalable model checking techniques. As we all know, model checking is highly automated. It's very nice. It has a lot of attractions, but scalability is definitely one big limiting factor for applying model checking to a lot of these interesting real world complex designs. Now, what we have done so far in terms of developing algorithms and tools is the development of these two tools I have listed here. The first one is called VeriPack. So the VeriPack is actually a refutation-based tool for verifying adversarial robustness of DNNs. So I'll talk a little bit more about this. Then the second one is Stamina. So basically, Stamina is a tool where we apply state-space truncation techniques to model check stochastic behaviors of infinite state continuous time Markov models. So Stamina has been heavily used for the verification of a lot of our synthetic biological models. Now let me then mention our DNA verification tool. So basically here we apply partition to the high dimensional input. Usually the input we focus on right now includes like images. So because they are high dimensional, so our tool will actually automatically partition those. Therefore, it can allow abstraction and verification in parallel. Then we actually came up with this randomized fast gradient sign method, or FGSM, as a way to apply abstraction to each partitioned input region, so that we can use this tool to efficiently find robustness violations before we actually revert to formally verifying a given input, whether it has adversarial examples or not. This VeriPack framework also applies enumerative verification technique, basically scales directly proportional to the region size. So our idea is that we partition the region, and then we use refutation-based approach first to quickly generate a lot of these adversarial inputs, and if the adversarial input generation fails, then by the time we have to apply verification, the region is already small enough for us to do the verification. The other feature of our VeriPack tool is that it can produce a covering set of adversarial inputs, and we have found that this feature is very useful because we could actually harvest those adversarial inputs to retrain our neural network, so that the robustness can be improved quite significantly. So then for the network on chip verification work, we have two sub areas. The first one is on the fault tolerance network on chip verification. So fault tolerant knock has basically been applied in safety critical automotive applications. Basically, people have tried to have this dependable network on chip platform, so that they can actually form a network for all the electronic control units in a vehicle. So this is better than having each ECU tied specifically to a sensor or an actuator, because if one ECU fails, then through the network, other ECUs can actually make up the function, so that the whole design is more robust. So the other nice feature of forming a network on chip of these ECUs is to allow power to balance, right? So however, to design a fault-tolerant routing protocol for in order for the network on chip device to work, it has proven to be very complex and error-prone. So what we did is that we actually modeled a fault-tolerant routing algorithm using the Ivy, formal specification language. And we also automated the counterexample guided invariant augmentation, so that the idea is that we actually would trick Ivy to give us, as many counterexamples as possible, specifically to the problem of, live log freedom. So a live log freedom basically for a NOC is where, we can guarantee that on the NOC, you can never have a packet that would, get trapped forever without ever reaching the destination. So we want to avoid, the existence of live log in, the fault tolerant routing design, because, those packets will be just there creating more traffic and then consuming power without doing anything useful. So we were able to discover and correct, live log issues on actually a large scale NOC because of, the way that we model the, the system. And also, I should say, it's also because the scalability, capability of the Ivy, model verification tool. And we also came out, or we also developed an incremental abstraction technique to scale the live log freedom verification up to an arbitrarily large network. So the other area of NOC verification is to look at the probabilistic verification of NOCs. Mainly our work has been focusing on using probabilistic verification to analyze the power supply noise on a NOC. So power supply noise actually gets created when you have multiple devices switching simultaneously. So it's unavoidable. But on the other hand, PSN usually worsens the reliability and performance of on-chip communication. So the goal is to design a NOC where we can minimize the PSN. So we attack this. We tackle this problem by looking at by using the probabilistic verification of PSN. So we have done this for a 2x2 mesh network on chip system, and we actually assumed some uniform random traffic loads. And from there, we were able, or in this work, we were able to actually come up with an abstraction technique called probabilistic choice abstraction. Basically, the idea is that we delay the enumeration of random variable values in our model to the point where they are evaluated. So in this case, we actually were able to control the state space growth, but basically from exponential to polynomial. And from this work, it also reviewed an efficient network packet generation pattern where we could achieve 0 probability for the PSN events. So so how then I had this slide. I thought how could my research contribute to the app to the research in Blimp's design. As you can see, a lot of my work has being centered around the model-based design methodology. So definitely, I believe, we can apply model-based design methodologies for LIMS design as well. Then also thought about deploying probabilistic verification techniques to, for example, to check that whether the constrained energy requirements can be met, given some control and planning strategies. So probabilistic verification is definitely, good at doing these quantitative analysis. Then the third point is that, probably we also want to think about appropriate formalisms and abstraction techniques for, modeling this large possible and, large environmental disturbances, because whenever we design something, we need to model the environment so that we can actually fine tune our model. In my research, I've used a lot of different abstraction methods, and I'm sure those methods can also help in this in the research in this domain. Basically, again, it allows scalability for formal analysis. Lastly, I thought about this. So I'm wondering if blimps also have, ECUs like what we have in the vehicles. And if they do, is there some potential of putting them on a network on chip platform so that they can actually talk to each other? And then our experience of, verifying, fault tolerant network on chip protocol might be applicable to, to this problem. So with that, I like to end my talk and start to answer questions. Thank you.
Thank you. Any questions?
So I have a question. So after you had this you were talking about neural network verification, you had this parallelized algorithm, then you had this randomized PG
FGSM, right?
FGSM, yep.
Yeah.
And then you said you were going to do formal verifications. How do you do the formal verification step?
So we actually right now we're just testing, the points in each region. And again, we hope that by the time we need to do verification, we have small enough regions so that we can enumerate each point and then just check if they result any adversarial examples. So it's very primitive right now. But our framework was designed, with the hope that we could integrate other verification, methods into the framework so that maybe, we can improve there. We're also thinking about, coming up with more efficient verification methods. Yeah.
Great, thanks.
Yeah.
I mean, there's several tools that you could try if you want to use something off the shelf. All right, so. I think in the summer we ran like a competition for neural network verification.
Right.
So
right.
in the comp, you could use any of those or all of those could be possibilities.
Right. Yeah. So I guess the biggest issue is, the effort in integrating it into our design. So we have actually recently rewritten our VeriFpack tool so that now it can read the ONNX formats of neural network, and we're gonna try on the VNN benchmarks soon. Yeah, we hope to provide, as many useful adversarial examples as possible first. Yeah, because that could be really useful in retraining. Yeah.
Great, thanks.
Yeah, thanks.
So I think Georgios, you're up.
Here we go. I was thinking, what can I talk about blimps? And so I said, okay, let's look at disturbances, since these are notoriously, these are vehicles that are notoriously subject to disturbances in the environment. And so when you have this level of uncertainty, when you do motion planning and you would like to have some safety guarantees, then you have to take risks. That's the premise of my discussion today. And I pulled a few slides from various presentations that we have given in the past on how we can incorporate this type of risk into our planning. So just as a grounding example, I have not worked on blimps before, but we have looked into how currents change, for example, in the sea, right? So the the agency that oversees the currents in the oceans publishes these maps, and for the same area in space, you can see that the currents change during the day, right? So you know that in some accuracy in the areas that you care about, but the bottom line is here we see that the currents change, and if you have smaller vehicles, clearly things will drift in a different way if you don't have this information incorporated. So you may ask the question, okay, can I make these areas small enough? I know the drift in that particular area, and then I have unsafe regions and goals, for example, that I would like to achieve, and your goal is to compute a plan over this region so that you minimize the risk of entering the unsafe region plus maximizing achieving your goals. Similarly, when we drive on the highways, we have to change lanes and so on, then we have to assume some risk, because there is, if you are deciding to be 100% safe, you would just stay in your lane, you would never merge to the next one unless the road is completely clear. So you need to incorporate this type of risks. And so I'll present a couple of works. Again, I just pulled slides, so I'll have to skip a lot of things to stay under 10 minutes. So the first one is using stochastic barrier functions. And here the goal is to compute control actions that bound the risk of collisions in the presence of dynamic and static obstacles. That's the main goal here. Again, it's not to guarantee always that you're safe, but actually to bound the risk of collision. And why, you may ask, this is important, you get less conservative robot behavior. You can adjust the risk based on the application scenario, and you can also help formulating assurance cases. Since we know that the world is noisy, if we say, okay, this is how much risk I'm willing to tolerate, then you can establish an assurance case saying, this is the risk I'm going to tolerate, and here's the guarantee, mathematical guarantee that I actually take that risk. So for this next few slides, we can pose our robot vehicle problem in the affine control system form that is very popular with control barrier functions. And as one case here, we can assume that the obstacle motions in the environment, the dynamics are known, but they are stochastic. We have, for example, some white noise. We can formulate now a big problem, and we can write our safety regions. And now the difference is that we would like the probability that the system will enter an unsafe set to be bounded in some form. That's the main difference here. We have, again, our safety set, but the probability, the risk, we refer to the risk here informally as the probability of collision. And I'm highlighting this here because risk has many different interpretations that are all informal. So here's our definition.
Isn't the quantifier should be there exists, not for all?
Yeah, don't read this as it is there exists. It's not.
Okay.
It is for right.
some.
Yeah, that's a typo here. Absolutely. Thanks. Now you can formulate the quadratic programming formulation that is the standard in control barrier functions. And now we have a couple of new terms that, if you look at the paper, effectively bound the risk of collision. Plus, we add some term to reach whatever goal set we might have. And you can prove that if you do this, then you can bound the risk for collisions. And now I'm going to move to examples. Here's a simulation for that. So you have this robot moving among humans, and we are solving this optimization problem online, actually real time. And interestingly, when the risk, the robot is aggressive because we have let it take a lot of risk, but when the people came too close, it moved back, right? Just to avoid the collision, which is a nice feature. There was no kind of logic saying, okay, if you're too close to humans, then move back. Now, here is also a scenario with cars moving around. So the car is changing lanes while keeping the risk bounded, which is one of these graphs here. I don't remember here. I think this one. This is the risk. And the risk increases when you take a maneuver, you change lane. I think it's because you are entering in an area where you might actually encounter some collision. I can play this video again later. Now, the challenge with this formulation is that we need to know the model of the dynamic obstacles. So if you want to relax that assumption, then you have to move into a framework where you have to sample the space. So now you don't anymore just solve the quadratic program. You have to explore your search space using some sampling method, and now solve locally these quadratic programs that satisfy control barrier function constraints. And you don't use anymore a model for the motion, like in the sense of stochastic differential equations, but we have to have potentially a motion prediction, like as a probability distribution, where the obstacles might be over the future. And you can build that model using any other technique that you build these models, as long as these techniques give you probability distribution now. And you get similar results in terms of guarantees. And here's a simulation. Actually, I'll go to the second example. It's a little bit more interesting. So here we have multiple people. This is how the trees grow. This is happening in real time. So it selects paths that minimize the risk of collision. And I guess maybe I should have played also the actual, what you observe when the robot moves around. The interesting part, I guess, is here when the robot has to interact with the humans. Is there another? Okay, here's another human coming by, changes direction, and the robot doesn't have to stop, for example, even though the human appears to be going towards the robot. Finally, one more item here. What happens if you have uncertainty in terms of air currents, things like that? So in this case, the uncertainty is in the affine dynamical system, and we would like to design a controller that now behaves safely, or at least bounds, restricts the risk, even though we have here uncertainty. And here I'm not going to say probabilistic uncertainty, I'm going to say in the sense of non-deterministic. And you can solve this using, you can formulate as a linear program to find the worst case scenario under this uncertainty for every control step. And again, you can formulate it and solve it. You can formulate now the forward invariant set that would guarantee safety for your system under this non-deterministic noise. Moreover, you can do this also for higher order control barrier functions, which is important because blimps are actually do need higher order barrier functions. The challenge here is that in order to do this for higher order for higher order barrier functions, you need to solve a nonlinear program, which is expensive. So what do we do then is we are actually using neural nets to learn the solution of the quadratic program. So the quadratic program is solved offline, and the data produced are used to train a neural network. Now, if you do this as is, then the neural network that you get is not robust enough. So you have to use a Dagger algorithm where you need to aggregate the data. And I mean, if you're familiar with the Dagger algorithm, that's what we're doing here. And here's an example. This is now a kind of a boat, and it's operating with an unknown current over the environment, and it needs to avoid these obstacles. So we solve the control problem starting anywhere from this initial set. You need to reach this goal set while you avoid these regions. And you have, of course, this unknown current. So you solve it, and then you train the neural network, and we see that the neural network successfully manages to avoid the unsafe regions while reaching the goal. Of Of course, we don't have the proof that this holds for all initial conditions, but it will be interesting to combine this type of work with actually the work that just Chuchu presented that is will provide such guarantees. All right, what are the blimp complexities? Since nobody presented the dynamics of the blimps, I had asked my students to look at it, and I was disappointed of how complex this is, 6 degrees of freedom. And they were showing to me slide after slide of the dynamics, and you have the airship dynamics. This is a 6-dimensional set of equations that include gravitational, aerodynamic effects, kinematic terms. And then you have also the kinematics, another 7 dimensions here with quaternions and Cartesian coordinates. And you have also the dynamics of the wind, and you put everything together in a big dynamical system that is extremely hard to control. So from our perspective, what are the challenges to apply whatever I presented on this? This is high dimensionality of the system, which means, let's say, if you're going to apply online control solvers, online optimization, model predictive control, online RRT exploration is going to be time consuming. So you may want to learn the control barrier functions or the optimal solutions. We have different relative degrees between the output and the inputs, which means usually we'll have to design reference trajectories for the system. And of course, we may or may not want to include some model of the nature of the wind here. Path forward, I see having hierarchical control and using MPC type of techniques with neural network-based control barrier functions so that you follow the trajectories that you have produced from the hierarchical control. That's my hypothesis here. Of course, until you do the work, you cannot know what's true. Finally, since Aditya was talking about certification in the beginning, I would like to throw one slide here on how we do certification. For now, we are participating in a DARPA ARCOS program, and the goal here is to use falsification in order to do assurance or certification for these systems. And this slide here presents how search-based testing or falsification fits within DO-178C. So we start from high-level requirements. We use these high-level requirements to create both normal range test cases and robustness test cases, which is the abnormal situations. Through the formalization, of course, you detect issues with consistency in the requirements themselves. And if you have access to the source code, you can also cover the usual requirements for DO-178C, such as MCDC coverage, branch coverage, and decision coverage, whatever else you need in terms of your requirements. And now, in addition, what we provide is probabilistic guarantees on the presence and absence of defeaters. So this is now a new component that doesn't fit naturally within DO-178 in the sense that nobody talks about functional correctness. And the question here is, if somebody gives you a result for functional correctness that involves probabilistic guarantees, what do you do with that? How does it fit within your risk and hazard assessment in the overall picture? All right, this is all I wanted to talk about. I know I went fast, but I utilized some of Husam's time, so I need to thank him for that when I see him next time. Thanks.
Yes, several of you, you can give some grief and or thank him for giving you some extra time. Any questions for Georgios? And thank you for finally putting up some blimp dynamics.
All right, then I need to close my slides. I forgot about it. Right. Look, a nice picture of the.
Yeah, thanks, Georgios. This was a lot of interesting info. I don't think I have a question, but I would say one thing that I touched on the same thing was the dynamics of blimps. Why are they so complex? They're complex because they're done exactly like they're done for aeroplanes, like F-16 or something. But do we need that? Because if you look at a blimp actually flying, you'll just see something nice splines or something within disturbances. We don't.
Well, the F-16 will not stay in hover, right? Maybe we can compare with F-35, but and when you stay in hover, then you need to adjust your propulsion, let's say, to stay there, right? Because the currents will be. I mean, the helicopters do that anyway, right? But I guess the order of magnitude of the dynamics is different. You cannot assume that you will have enough thrust to keep you there where you want to be potentially.
Yeah. Yeah, but the thing is, like, do you need all that complicated structure to talk about simple behaviors that actually emerge from a blimp?
Yes and no. Maybe no if you have good tracking controllers, but you'll see that the blimp might be in a strange position. Let's say you track a circle, but because the currents push the blimp in certain direction, you might not follow the direction you want. The blimp might be rotated and flow around in space. So you have too many degrees of freedom there that you may not be able to control directly. And that's why you have the difference between inputs and outputs in terms of the dynamics. You cannot have direct influence there.
I do have a question.
Yeah.
Yeah, Cody, go ahead. I think.
Oh, sorry. So I had a question about like the speed of the dynamics. So if you linearize the system and look at the eigenvalues, for example, and I was thinking about, because you're looking at ships and maritime navigation, which those dynamics are relatively slow compared to like an aircraft, which is good on one hand, but also requires potentially early action, right? It's like, if I identify this paddleboarder going in front of my ship, 10 seconds before, I don't have enough time.
Right.
So can you comment on that type of problem with respect to blimps? Is it even worse than ship navigation, or is it faster, slower?
Right. I am not a blimp expert.
You put equations up.
Right. Well, my students did that, so. Well, I mean,
I mean, it depends, right? But I guess I was curious, like, how much of a problem this is now for prediction versus control versus reaction, I guess. Maybe this is for everyone, not just for you.
So I think I'm not a blimp expert either, but you do have this idea of proactive control, and this probably shifts it more because of the under actuation and the large disturbances. You just end up with more proactively controlling. I guess in reachability terms, you just have a tube that becomes larger and larger if you project in time, and hence you'll have to take stronger actions early on. That's my guess.
Yeah, and just to be clear, one of the reasons we kind of liked balloons and blimps as a topic is because there don't appear to be very many deep experts into the dynamics of balloons. So